Hello guys, in this video, we are going to transition to a new theme of this course, that is using R programming for data science and business analytics. Despite having some data or business analytics examples, our previous lectures have largely been about R's programming constructs. The curriculum was designed this way because I want to ensure every student has been armed with necessary skills of R programming before stepping forwards to learning about how to use R to tackle data science or business analytics problems. And now you should be ready. And this video will mark a shift to data science or business analytics with R. Our first step towards data science is to learn a consistent way to organize our data in R, an organization called tidy data. Getting our data into this format requires some upfront work, but that work pays off in the long term, because once we have tidy data, we will spend much less time monkeying data from one representation to another, allowing us to spend more time on the analytic questions at hand. To start, let's consider an example to see how data organization could go wrong with a regular data table. In practice, most data sets are rectangular tables made up of rows and columns. The Billboard data set shown here records weekly ranks of songs appearing in the Billboard Top 100 over a certain time period. It has variables for artist, track, length, genre, and date when a song entered the chart. And since then, its weekly ranks is recorded in the following 64 columns, from week 1 through week 64. The current format is useful for data entry and presentation. This format represents a convenient way to record regular spaced observations over time. It also reduces duplications, since otherwise each song in each week would need its own row, and a song's metadata, like artist, title, and genre, would need to be repeated across rows. However, with this presentation format, you may find more and more missing values as we go through the columns for weekly ranks. And the result of this code can show this clearly. This is because not all songs that had broken into the chart had the same level of popularity and stayed in the chart for the same amount of time. If a song was in the chart for less than 64 weeks, the remaining columns are filled with missing values. Chances that a song would only appear in the chart for only a few weeks are high, so missing values are produced in this table in a structural way. Moreover, we may want to investigate the possible variation patterns of track rankings, as well as the factors that drive the surge and plunge of a track's ranking. A good way to tease out hidden patterns is to visualize the data, and we may want to generate a plot that describes weekly ranking variations among tracks as such. This plot uses week number as a variable for the x-axis, revealing that column headers in that table are actual values, not variable names. As you may realize, in practice, there are many ways to structure the same underlying data, but these different layouts are not equally useful for data analysis. For example, the same data on track rankings can also be presented in this long format by spreading weekly ranks originally contained in columns into different rows, and adding a new column that associates each rank with the corresponding week. Compared with its wide format, this long format makes the values, variables, and observations for data analysis clearer. It also eliminates those missing values. Next, I'm going to summarize several common causes that make a dataset messy or unready for data analysis. The first cause is to use variable values as column headers, as we've seen in the Billboard top hits example. The second source of messiness is that we store multiple variables in one column, as demonstrated by this data table. This dataset comes from the World Health Organization. It records the count of confirmed cases of a certain disease by country, year, and demographic group. And the demographic groups are broken down by gender and age, as represented by these column headers. For example, M014 stands for male and 0 to 14 years old, and is actually a combination of the values for two variables, gender and age. And a higher level messiness occurs when we try to consolidate observations of different levels in a single data table. For example, the Billboard dataset actually contains two types of observational units: songs and their weekly ranks. It leads to the duplication of facts about individual songs, and a song's metadata, like artist, title, length, and genre, was repeated as many times as the number of weeks it stayed in the chart. So the datasets need to be broken down into two datasets: a song dataset, which stores the metadata of individual songs, and a ranking dataset, which gives the weekly ranks of songs. And it is also possible that we use multiple tables to store variables that describe the same type of observations. Essentially, a dataset is a collection of values, and every value belongs to a variable and an observation. Whether a dataset is messy or tidy depends on how rows, columns, and tables are matched up with observations, variables, and types. While every messy dataset is messy in its own way, tidy datasets are all alike and has a specific structure, as described by these three principles. And tidy data provides a standardized way to link the physical layout of dataset with its semantics. So arranging our data in this way makes it easier to work with, because we have a consistent way of referring to variables and observations. And this underlying uniformity further makes it easier to design and use a cohesive set of tools for data mounting, visualization, and modeling, and smooths the overall data analytics workflow. Besides, recall that R is naturally vectorized, and most built-in R functions work with vectors of values. So storing variables in terms of column vectors allows R's vectorized nature to shine. And there's a popular suite of tidy tools known as the tidyverse, which is designed to work with tidy data over the entire course of the data science workflow. In all, if we ensure that our data is tidy and use these tidy tools, we'll spend less time fighting with the tools and focus more on answering our questions about the data. From now on, we'll spend several successive lectures learning the tools in the tidyverse collection for data mounting, visualization, and modeling. To start, I would like to first give you a brief introduction to the tidyverse collection. As we know, R is an old language, which means some things that were used for 10 or 20 years ago now perhaps get in our way. Although many fundamental data processing functions exist in base R, they have been a bit convoluted to date and have lacked consistent coding and the ability to easily flow together. To innovate the way of how R interacts with data, over the years, the R Studio team has been making great efforts to collate and reconcile data science activities in R. As a result, a lot of data science tasks are becoming packaged in more cohesive and consistent ways, leading to a collection of packages called tidyverse. The packages in the tidyverse share an underlying design philosophy, as well as grammar and data structures. They are designed to work together naturally. Some renowned members include the dplyr and tidyr for data wrangling, ggplot2 for data visualization, string-r for string operations, and many more. We can install the complete tidyverse collection by supplying this single keyword to the install packages function. Once the packages in the tidyverse are successfully installed, we can use the library function with this keyword to load the core tidyverse, which includes these 8 packages. Other packages with more specialized usages in this collection need to be loaded with their own library calls. An interesting thing about the packages in tidyverse is that they all have their own honeycomb-like stickers, kind of a metaphors indicating they share a common design philosophy, grammar, and data structures. One of the unifying features of the tidyverse is a common data structure called a tibble. Tables are a modern remake of the data frame and encapsulate only best practices for data frames that hold the test of time. A table can be created from column vectors with the tibble function provided by the tibble package. In this example, I create a tibble with 3 columns. If you are already familiar with the data frame function, the tibble function does things similarly. For example, it can recycle vectors of length 1. And an interesting feature you can observe from this example is that the tibble function evaluates these named arguments sequentially, so that we can refer to variables just created. For example, x and y here, when creating new variables, like variable z in this example. The tibble package also provides a function named glimpse, which is similar to the structure function and makes it easy to look at our data in a transposed view. Then, how is a tibble actually different from a data frame? First, tibbles have a refined print method that shows only the first 10 observations and fits all the columns on screen. It also reports the type of each column along the name. And tibbles never change an input's type, so there's no more this sort of settings needed. And tibbles never change the names of variables. For example, if you want to create a column label including a space, the data free function always replaces this space with a dot. But this undesired thing won't happen when we create a tibble. Moreover, Tables don't allow setting row names, so as to enforce the rule of storing variables in colons as opposed to as row labels. And the tables clearly distinguish between the single bracket notation and the double bracket notation. The single bracket notation, when used with a tibble, always return another tibble. So no more this sort of setting is needed. And if you want a vector as a result, you have to use the double bracket notation. A quick remark here is that in our subsequent lectures, I'll use the term tibble and data frame interchangeably, referring to tables. When I want to draw particular attention to R's built-in data frames, I'll call them data frames.